Welcome back, everyone. So we've already taken a look at several envelope controlled effects, such as a compressor, a noise gate. We recently looked at an envelope filter. And today we're going to be looking at another compressor, but this one uses a different mechanism for controlling the output of the signal. So if you remember, when we looked at a compressor, we looked at an optical compressor where we used a light-dependent resistor to change the gain of an op-amp stage. However, long before that was a common practice, MXR came up with this circuit called the Dyna Comp. This was all the way back in 1972, and it uses an operational transconductance amplifier, usually just called an OTA. And before we get into the circuit itself, I just want to highlight the OTA here. It is this piece, and if you look at it, I mean, it looks relatively like an op amp. We have a positive terminal, we have a negative terminal, and we have an output. But you'll notice that we've got these two circles here at the end that connect to a pin, which is a difference, but also the fundamental way that it works is different. So an op amp, or an operational amplifier, provides a voltage gain to a voltage input signal. However, an operational transconductance amplifier provides a current gain. So instead of amplifying the magnitude of the voltage, it is amplifying how much current is going through. And so we're not going to really get deep into exactly what that means, but it's just an important distinction between the types of devices. And we'll talk a little bit more about the OTA as we get into our circuit here a little more. So in this schematic, we have three main building blocks that we're going to be looking at. We've got our input buffer, that is this piece. We have the transconductance amplifier stage, which is this piece. And we have our envelope follower, which is this piece. Okay? And so we're going to go through each of these one at a time and kind of talk about what's going on and some of the characteristics of each of them. So to start with our input buffer, this is actually a very simple NPN BJT buffer stage. Okay, so I'm going to highlight it again here so that we can see what we're looking at. And so we come in on the input, we have a pull down resistor, we have a DC blocking capacitor, and then we have this input resistor to the base of our BJT. And the base of our BJT is being biased through this 1 meg resistor from this reference voltage that is right here. Now you'll notice that these two resistors are not the same value, which means that we're not just taking the input voltage, our 9 volts, and dividing it in half. Rather, we get more like 2.5 volts here. I'm not exactly sure why they did that. It's kind of a weird choice of a bias voltage, but a typical guitar signal isn't going to swing too far. And so, you know, we're not likely to run out of headroom with that 2.5 volt bias voltage, but it is kind of a weird thing. But anyway, that reference voltage comes through this 1 meg resistor to the base to bias our transistor. The collector is connected directly to power, and our emitter has a 10K resistor to ground, and we're taking the signal off of the emitter. So this is our emitter follower, right? And if you remember, the emitter follower has the characteristic of unity gain and non-inverting amplification. If you take the signal off of the collector, the signal is inverted, and you can get a gain of greater than 1. But if you pull it off of your emitter here, then we've got unity gain and it is not inverted. And then we have a DC blocking cap here before going on to the following stages. So very simple emitter follower buffer there. Pretty bog standard. The next stage of the circuit is the actual amplification stage, the OTA amplifier stage. And that comprises this piece here. Okay, so this piece is setting up our operational transconductance amplifier as just as kind of a basic amplification stage. All right, we've got a 1 meg resistor pulling down to ground. We have a 470K that is from our 9-volt line into this trimmer potentiometer. And you notice that this trimmer potentiometer has one leg that goes to the plus terminal and the other leg goes to the minus terminal. Now, one of the things about an operational transconductance amplifier that is really different from an op-amp is that what the OTA is amplifying is the difference between these two terminals. Okay? An op-amp is a device that is trying to always keep the voltage the same at the two input terminals and the output, but the operational transconductance amplifier is actually taking the difference between these two terminals and is amplifying that. And so in order to make sure that the device is giving you the best amplification swing with minimum noise requires that you carefully balance the input to each side. And so this bias voltage that is coming down here into this pot allows us to make very small adjustments to the bias on these two pins. Now, with ideal devices, this trimmer potentiometer here would be set exactly in the middle, and you'd have exactly 1K from our bias to the negative terminal and 1K from our bias to the positive terminal. However, that's not always the case. Sometimes you have slightly imperfect devices, and so this trimmer is just to allow you to make small adjustments there to really dial it in. I mean, if you compare the fact that we have 470K here and 2K here, it's pretty clear that really small adjustments can make a big change in really dialing in the balance on these two input terminals. Okay, so that's what this trimmer is doing. And then we've actually got off of the positive terminal here, we have a 1 meg to ground, but then we also have this arrangement of 2 caps and a resistor. So if we go through a resistor to a cap to ground on this leg, then what we have is a low pass filter. Okay, so what this is doing is it's actually rolling off a little bit of the high frequencies. And if we're rolling off the high frequencies of only one side of the operational transconductance amplifier, that means that the difference between them is bigger at the high frequencies, which means our output is going to exaggerate those high frequencies more than the low frequencies where this filter doesn't have any effect. Okay? And having this cap into this cap is going to provide, you can look at them as kind of a series thing, but really it's that, let me erase some of my markings here so that I can show this more clearly. So what happens is we've actually got these two components in parallel and then this guy. And so the presence of this cap is going to also change the frequency response a little bit. It's not Not a huge deal, but it is there. It will make a difference. If you want to see exactly what that does, I would encourage you to go simulate it in Spice or something. We're not going to talk about it just right now. So that is how we've set up the actual amplifier stage of the transconductance amplifier, right? But now we get to an interesting part of the circuit, which is our envelope follower. But the thing about this envelope follower, which I'm going to, let's see, outline like this. The interesting thing about this envelope follower that is different from the circuits we've looked at in the past is that this is what's called a feedback envelope follower, whereas the other ones that we have looked at to this point have been feed-forward envelope followers. Now, the reason that this one is a feedback envelope follower is because it requires our audio signal to go through the amplification stage before we even get our envelope. Okay? And the envelope is going to control the gain of this stage. So if we have a really sharp transient, then what's going to happen is that for the tiniest fraction of a second, our signal is going to come through our amplifier before it comes into our envelope follower, which then clamps down on the signal. And so you can get a little bit more of a transient before it clamps down on the signal, and this results in what can sometimes be called pumping of a compressor, meaning that hearing the effect of it actually clamping down is much more noticeable. If we were to have a feed-forward envelope follower, we would tap it off right here, and we would have our envelope follower circuitry here that would then come and control our amplifier, so that if there's a big transient in here, then right about the time that the transient gets to our amplifier stage, it's also going to receive a control signal saying, hey, turn the signal down, reduce your gain. Okay, so this is what a feed-forward envelope follower looks like as opposed to the feedback envelope follower that is here. And one is not any more correct than the other. They're just different. And so it really kind of depends on the effect that you want. So let's take a look at how this envelope follower is working. The output of our OTA stage comes onto the base of this transistor. We notice that this transistor has a 10K resistor here and a 10K resistor here. Because these resistor values are identical, that means that the signal here and the signal here will be equal in magnitude, but they will have opposite phases, because this guy is going to be in phase and this guy is going to be out of phase. Okay, if we have a signal like that coming in. And so the reason why we have one out of phase and one in phase at exactly the same amplitude is so that we can rectify the signal and get the bottom half of the waveform and the top half of the waveform and combine them together to give us the overall envelope of the signal. So what do I mean by that? So what ends up happening is that our signal comes here. It gets split. This is often called a phase splitter because it's equal magnitude and opposite phase. In fact, if we were to swap this out for a tube, that would be exactly what tube amps do prior to sending the signal to a push-pull pair of tubes in an amplifier. And then we have two identical pieces of circuitry. We have a DC blocking cap here, okay, because we've got a bias voltage sitting here, and we don't want that bias voltage. We just want the AC signal, because that's our envelope that we want. So we block the DC, and then we have this 1 meg to ground. We have a resistor, or not a resistor, a diode here, which is going to make it so that we're only taking the positive half of our waveform, and then we put it onto the base of this transistor. The emitter is grounded, and we're taking the signal off the collector. Now, because we're doing the same thing with both the in phase and out of phase signal, what we end up getting is no matter which half of the wave is positive, we are rectifying that half of the wave into a DC voltage, so that we can use that to control our amplifier. Okay, because this signal is going to come in here and it's going to go like that. The two signals are summed together here. They add together here. This capacitor right here is going to stabilize this voltage. It's going to filter it so that it's DC. And this resistor right here acts not only to provide the power to our transistors, but it also serves as it's also going to serve as controlling the attack of the compressor. Okay, because it's going to govern how quickly this cap can charge after it has discharged. Okay, so by the time we get to here, we've got ourselves a DC voltage that relates to our envelope, so that if we have a negative swinging signal, then this half gets rectified to a positive voltage. If we have a positive swinging signal, this half is going to rectify that to a positive voltage. So we always get a positive voltage here. And the reason we want a positive voltage here is because we want a positive DC voltage that we can send out this direction into the center of these two circles. Now, those two circles can be a little confusing, but the thing to know about an operational transconductance amplifier is that where it shows those two circles, that is actually a control current point, meaning that, oops, I wanted to keep that line, meaning that if we apply a current onto pin 5 of this chip, but if we apply it here to the control current, it will actually reduce the gain of the amplifier. So we set a static gain of the amplifier for how much we want it to amplify, but then if we put a current here, we actually reduce the amount of amplification that happens. And so when we have a DC voltage here, we're taking it, you'll see that we've got, we're tying the collector of this transistor to power, and we're taking the signal off the emitter, which means that it's going to be in phase. This potentiometer is going to control the sensitivity, because it's going to govern how much of our voltage becomes, because we have a fixed voltage here, and we can change this resistance, then using Ohm's law, as we change our resistance here, we're changing how much current flows into this pin. Okay? So we have a small fixed resistance here, so that even if this thing is completely dimed, we still, have some amount of resistance, so that we have some amount of current going through it. But it's small compared to this, so the pot dominates the control of how much current there is. So we take our voltage through here. The resistor controls how much current it's sinking, and that current comes down into this control pin. And the more current we put in here, the more this OTA is going to reduce the volume, or reduce the amplitude, right? So that's how this envelope detector and OTA stage work together, is we have an output signal that gets negative swing rectified, positive swing rectified, filtered into a DC voltage. DC voltage goes through a resistor that limits the amount of current we sink, and that current goes back into the OTA to change what its amplification factor is. Okay? And the last part of the signal path that we have is actually for the output, because you'll notice that after our OTA stage, we have off of our transistor here, we're also taking the signal off the emitter, so unity gain, and we've got a DC blocking cap. We go through a resistor, which as we send this current through a resistor, it's going to govern what our voltage is. And then, since we've got our output as a voltage here, then we have this volume potentiometer that goes to our output jack. Okay? So if we were to do just like a super quick recap of everything that's going on here, it would look something like this. We come in through a unity gain buffer. This signal comes in and we are sending it to the plus and minus terminal. Because we have got this potentiometer here and these components here, we're actually making it so that the positive terminal and negative terminal are just a little bit different so that we have a difference to amplify. That output comes out through a phase splitter where we split our signal into the positive half of the waves and the negative half of the waves. We combine those so that we have a single DC voltage that represents the absolute value of our envelope. And then we buffer that DC. We send it through a resistor that governs how much current we can sink. That current tells the OTA to turn down the signal when it's large enough. And then we also take our output signal to our jack like that. Okay? So hopefully that helps to demystify a little bit of what's going on in this circuit. It's one of those things where the operational transconductance amplifier can be a very mysterious component, but even though I have glossed over a ton of information, the important thing to remember is that it's going to amplify the difference between our two terminals and turn it into an output current because it's a current amplifier, and that if we put a current in on the pin that corresponds to these two little circles here, I don't even know what they're called, that acts as a control current that will actually reduce the overall amplification of the stage. And that's what our envelope detector is doing. I hope you found this useful. If you have not seen the video on the optical compressor, I recommend you go take a look at that. It shows a different envelope follower technology or topology, and hopefully you find these interesting. And until next time, take care.